I swallowed a dictionary whole the other day. It was the sorest throat I ever had. Hey, you know what? This one time I went to Five Below and I bought a dictionary and all the pages were blank. I had no words to describe how upset I was. All right, folks. Well, let's talk about what it means to be orthogonally similar. We say that the square matrix B is orthogonally similar to another square matrix A if there is an orthogonal matrix P such that B is equal to P inverse AP. All right, and we have seen that expression before back in chapter 5 when we were talking about diagonal matrices. But because we're assuming that P is orthogonal, based on yesterday's discussion, this would imply that the matrix B is also equal to P transpose AP. All right, recall if A is orthogonal, then A inverse is equal to A transpose. That was one of our definitions of what it means for a matrix to be orthogonal. So in this case, P is kind of serving as, the letter for the matrix instead. And so P inverse AP is equal to P transpose AP. Now, we would say that A is orthogonally diagonalizable if it's orthogonally similar to a diagonal matrix. In other words, if we could get a diagonal matrix by doing P transpose AP, giving us D, which is diagonal, then we say that the matrix A is orthogonally diagonalizable. So in this case, P transpose AP, which is the same as P inverse AP, should give us a diagonal matrix. And much like back in chapter 5, the entries along the diagonal matrix will be the eigenvalues. Now, I was thinking about this before class. I think what I'd like to do is skip going over the theorems for now, show you how to orthogonally diagonalize a matrix, and then we can revisit the theorems to see the connection between our results and what the theorems are stating. So we'll come back to these theorems and verify them with our example. But before we start that, here's the process that we undergo for orthogonally diagonalizing a symmetric matrix. Yeah, could you imagine trying to say that 5 times fast? That's definitely a tongue twister. Which, by the way, a tongue twister, the world champion of tongue twisters, he ended up in jail this past weekend. They gave him the toughest sentence, I'm telling you. All right, so it does boil down to 3 major steps. Okay, there's a little bit of work involved, but here's what we're up against. Number 1, we want to do is find a basis for each eigenspace of the matrix A. All right, so we have to find the eigenvalues of the matrix A as well as the basis vectors. Now, in some cases, you might get 2 or more basis vectors. And if that's the situation we land in, then we have to use the Gram-Schmidt process to make sure that the basis is an orthonormal basis for the eigenspace. All right, I don't mean to give you any bullshit or anything like that, okay? But once we do that, these basis vectors, which are orthonormal, okay, so dot product is 0 and norms are 1, those basis vectors will form the columns of P. Okay, so form the matrix P, whose column vectors are the vectors from step 2. Let's get to work. All right. So in this one and only example for this section, which I'll take a poll and see if you want to do some more afterwards, we're going to find a matrix P that orthogonally diagonalizes the matrix A, and then we're going to need to determine P inverse AP, which life is a little bit easier on this regard because P inverse is the same as P transpose. Okay, so it's quite easy to calculate the inverse because P is going to be orthogonal, which means that the inverse is the same as the transpose. Now you'll notice that we have a symmetric matrix. Okay, here are the entries along the main diagonal, and those that are across the main diagonal from each other are equal. So it's worth noting that this is a symmetric matrix. We'll see why that's important when we revisit those theorems. Now, in order to find this matrix P that diagonalizes the matrix A, we'll have to start by forming lambda I minus A. All right, and you may recall the shortcut to that. It's always lambda minus the entries along the main diagonal. So we'll have a bunch of double negatives there. And what do we do to the entries off the main diagonal?
We put a negative there.
You got it. We negate them. So the rest of row 1 is going to be negative 2, 0, negative 2, and 0 again, and then 0, 0, lambda plus 5 for row 3. All right, let me break this off so that we can do a step 2. Step 2 is going to be to take the determinant of the matrix we just formed, set it equal to 0, and solve for lambda. Now, even though it's kind of close to a diagonal matrix, it is not a diagonal matrix, so we can't just multiply the entries along the main diagonal. We would have to do cofactor expansion to form det lambda I minus A. And I'm going to go with row 3 for this cofactor expansion, which means we'll have to write out lambda plus 5. I'll put it in parentheses. And this is going to go in front of the 2 by 2 submatrix, which is formed by getting rid of row 3 and column 3. So we're going to have these 4 as our entries inside of the determinant bars. And I'm actually going to bring this up here to save on some space. We would be looking at lambda plus 5, and in brackets, crisscross multiplication would give us lambda plus 3 quantity squared minus 4. Now, when you simplify lambda plus 3 quantity squared minus 4, you get a quadratic. It looks like lambda squared plus 6 lambda plus 5. And that quadratic you're going to want to factor, and it factors as lambda plus 5 times lambda plus 1. So we get a duplicate eigenvalue. We have negative 5, another lambda equals negative 5, and then lambda equals negative 1. So these right here are the eigenvalues. Let's go ahead and find the basis vectors for these eigenvalues. We'll start with lambda equals negative 5, and then I'll have you work on lambda equals negative 1. Okay, so let's do lambda equals negative 5. And remember, we're going to augment lambda I minus a with -5 in place of lambda with the 0 vector. Now, if we use -5 and lambda I minus a, okay, each lambda turns into -5. And in the first row, that would give us -2, -2, 0, then -2, -2, 0 again. And then the bottom row will be nothing but zeros. The RREF version of this matrix is as follows. The first row is 1, 1, 0, 0. And surprisingly, the rest of the rows are filled with zeros. We're then going to want to bounce into a parametric equation setting, right? And let's imagine that column 1 is for x, column 2 for y, and column 3 for z. I have a question for you. How many parameters are required to write out the solution? Well, let's look at our one and only leading one that corresponds to x. So y doesn't correspond to a leading one, nor does z. So it actually turns out that we need two parameters. I'm going to let y equal t and z equals s. Now, this gives way to a solution vector, and I'll take it. I'll do some intermediate steps here. Row 1 would tell us that x is equal to -t. All right, and that comes from rewriting equation 1 as x plus t plus 0 equals 0, and then isolating x by subtracting t over. Then we define y as our parameter t, and then z as a parameter s. Now this is all going to get blended into a solution vector that we could actually split up as a sum of two individual vectors. One vector involving the parameter t, and the other vector involving the parameter s. So I'm going to start with the parameter t, and I'm going to place it in front of our first basis vector. If we look at the entries of the first version of the solution vector, we have -1t, +1t, and then no t's in the third row. So what that means is that the first entry, once the t is factored out, and these are split up, is going to be -1, then 1, then 0. And then the solution vector for corresponding to s, the part of it, is going to be 0, 0, 1. And so these two vectors right here, -1, 1, 0, and 0, 0, 1, those help form our basis. Which I'm going to write in set notation. The issue that we have with this basis is that it's not necessarily orthonormal. Okay. Now, if you form the dot product with these two basis vectors, and yesterday I kind of talked about how you could do it with the column vector version. If we wanted to dot these, then we'd multiply corresponding entries together and add them up. And as you would see, it would give us 0 plus 0 plus 0. So these two vectors are at least orthogonal. Okay, they're perpendicular to each other. So that's not really an issue. What the real issue is that this vector has a norm that's not equal to 1. So in order for a basis to be orthonormal, remember, the dot product of all vectors has to be 0, and the norm of each vector has to be 1. Okay, the norm of the second vector is fine, okay, but the norm of the first vector is actually different from 1. And so I'm going to add on to this ON basis. And we're going to have to normalize this very first basis vector by dividing each entry by its magnitude. Does anybody want to offer the magnitude of this first basis vector? It is the square root of 2, yep. So let's take -1 and divide it by the square root of 2. We'll take +1 divided by the square root of 2, and then 0 divided by radical 2 is still 0. Now the norm of the second basis vector is 1, so there's no need to unitize it. You'll actually end up getting the same looking vector. And now we have an orthonormal set. Okay, so this set of vectors right here that's in the light blue are orthonormal vectors. And these are going to form our first two columns of the matrix P. So the first basis vector will be P1, second basis vector will be P2. Your mission, should you choose to accept it, is to find the basis for lambda equals -1 and ensure that the basis is orthonormal. Okay, so I'll give you a few minutes to work on this. We'll go over the results, and then we'll construct the matrix P. All right, so I'll start writing out the solution that I have. So when lambda is equal to -1, lambda I minus a attached with 0, the 0 vector that is, will give the following augmented matrix. Which when you RREF this, you're going to get 1, -1, 0, 0 for the first row, 0, 0, 1, 0 for the second, and then all zeros for the third row. How many parameters this time? Sammy, if you want to redeem yourself.
1.
Oh yeah, you got it. Yep. Yeah, there we go. Nice. So x corresponds to a leading one, and so does z. So it looks like y is our parameter. And based on the first row, x would equal positive t, y would equal t, and then based on the second row, z would equal 0. So we could mesh this into a solution vector, tt 0, and factoring the t out gives us a basis vector with entries 1, 1, 0. So a basis for this eigenspace would consist of this vector 1, 1, 0. And would this vector be good to use in our matrix P?
Yeah.
Okay, so there's no other vector to check that it's perpendicular with, so that's kind of covered for us automatically. But what about the norm of this vector? Let's look at the norm of 1, 1, 0. That would be 1 squared plus 1 squared plus 0 squared, square root of all that, which is the square root of 2. So the norm of this basis vector is not 1. So we are going to have to take an additional step where we form an orthonormal basis by dividing each one of the entries by radical 2. Oops, that should be 0. Derp. So this is actually what the third column of our matrix P should be. And at long last, I'll separate this out, kind of in the style of Tetris, or maybe this is kind of like a sonic map. Here we go. Sonic the Hedgehog. I should probably add some red in there for his shoes, right? Okay, so anyway, we're going to go ahead and construct the matrix P, not B. And this is going to be formed by taking our vectors P1, P2, and P3 and lining them up as columns. And we're going to use the orthonormal version of the vectors. So the first column is -1 over radical 2, 1 over radical 2, and then 0. Second column is 0, 0, 1. And third column is P3, which corresponded to lambda equals -1. Okay, so this would be the matrix P that orthogonally diagonalizes the matrix A. Now for P inverse AP recall that since P is orthogonal, this is the same as P transpose AP, which we know should give us the diagonal matrix D. Now D is going to be a 3 by 3, since there were 3 eigenvalues. 2 of them were duplicates. And the first 2 columns correspond to the eigenvalue of -5. So because of that, the first 2 entries along the main diagonal will be -5. And then the last column corresponded to lambda equals -1. So the third entry along the main diagonal will be -1. And then since this is a diagonal matrix, the rest of the entries will be 0. Okay, so any questions so far? Let's go back to page 1 and discuss these theorems. See whether or not some of them check out. So we'll start with the first theorem. It says if A is a square matrix, then TFAE, okay, meaning that the following are equivalent. The first one says that A is orthogonally diagonalizable. So if this is true, then it means that A has an orthonormal set of n eigenvectors. Now, this is a there exists statement. This doesn't necessarily tell you what they'll be, nor does it tell you that they're going to automatically be orthonormal when you find them. It just says that with your eigenvectors, there should be a way of making them orthonormal. Okay, so this is more of a there exists. The other result is that A is symmetric. And in our example, on page 2, we actually started out with A being symmetric. So that means that we should have an orthonormal set of n eigenvectors, and A should be orthogonally diagonalizable. Okay, which basically means that the matrix P exists. And going back to our example, we do have a symmetric matrix, and we were able to construct eigenvectors that were orthonormal to each other. Okay, so the vectors P1, P2, and P3, you could check that they're actually all orthonormal. Not only is P1 perpendicular to P2, but P1 is perpendicular to P3, and so is P2. And the norms of all those vectors is equal to 1. So that would mean that the set of vectors P1, P2, and P3 would be an orthonormal set. So I'll make that a note. P1, P2, P3 is an ON set. Okay, so those 3 vectors form an orthonormal set. And those are the results of the first theorem. The results of the second theorem say this: if A is a symmetric matrix with real numbers, then the eigenvalues of the matrix A are all real numbers. And it says that eigenvectors from different eigenspaces are orthogonal. Let's go back to our example. notice that all of our eigenvalues are real numbers. Now this implies that if you have a symmetric matrix and all the entries are real numbers, which we have here, it means that you'll get, or it means you won't ever get imaginary answers for your characteristic polynomial. Okay, so none of your eigenvalues should have i's with them if your matrix A is symmetric with real numbers. And kind of a rehash of something we went over just a minute ago, the eigenvectors from different eigenspaces are perpendicular to each other. I'll add that as another note. That's basically saying that if we were to dot P1 with P3, we should get 0. And you can check that that's actually the case. Dot product of P1 with P3 gives you 0, and dot product of P2 with P3 gives us 0.